Kirchoff's rules are a set of conservation rules that allow us to determine quantities in complex circuits. Remember that there are two types of circuits, simple circuits. There is a series circuit that is a single closed loop of wire that contains a power source, usually a battery that provides a potential difference, and electrical components as resistors that utilize that energy. A series circuit has one closed pathway for current to flow and therefore contains one singular current flowing from the positive terminal through the circuit like this. We describe the current as being conventional from positive to negative in the circuit. It's important to note that the location of R and the location of V are irrelevant and that I is consistently exactly the same in every section of the wire. A secondary type of circuit is called a parallel circuit. A parallel circuit has a potential voltage source and then has multiple loops in which the current can flow, usually connected to additional resistors, more than one. In this case, the current that flows through the battery reaches a point here where the wires separate the current into two additional currents. And so in a parallel circuit, we'll call this I2, this first one would be I1, and then we'll call this one coming out of the junction going this way I3. In a parallel circuit, the energy is split at the junctions due to the connective conductive wires. However, since charge is conservative because what's flowing through the wires is actually electrons and cannot escape the wires, when I trace the pathway all the way around, I end up at a junction over here. And it should make sense that the current coming in from this side, which has flowed in this section of wire consistently the entire time, is I2, and then on this side has flowed around and is coming into the junction as I3. What Kirchoff has described is called the junction rule, and the junction rule is simply a conservation of charge. The fact that I1 splits into I2 and I3, but then upon completing the pathway, returns to I2 and I3 combining, coming out as I1. So no electrons are lost in the process. To state it more formally, Kirchoff describes the two rules as the loop rule and the junction rule. The loop rule states that the sum of the changes in potential around any closed path of a circuit must be zero. This is to say that voltage adds power and resistors take away power or voltage. Well, we can calculate that by the fact that Ohm's law tells us that voltage is I times R. And so we utilize this law in the statement above in order to analyze a simple circuit like what we've had. If you just simply take the loop that we have here with a simple voltage, a simple resistance, and a simple current, then the loop rule states that 0 equals the voltage minus I times R. And this confirms that by adding I times R to the other side, that the rule for Ohm's law holds for a simple circuit. Now, the reason why this becomes useful is if we go back and analyze this with multiple resistors built into the circuit, what you will find is that the voltage is simply I times a series combination of resistors. In other words, the R's factor out. And so that's where we get our equivalent resistance statements for our series and parallel circuits. In the junction rule, over here, at any junction, the sum of all currents entering the junction must equal the sum of all currents exiting the junction. Remember that this is conservation of charge, whereas this is conservation of energy. In the conservation of energy circuit, the voltage supplied by the voltage supply is entirely utilized by the electrical components on the circuit. All of the energy must be utilized. This is why it's a summation with 0. Over here, all of the electrons must be utilized. When the current generated by the battery flows through the battery and meets this point, it splits proportionally based on the resistance of each individual pathway. Now, the resistance could be simply one resistor attached to each pathway, but it could also be multiple resistors in series, just simply increasing it as an algorithmic addition. Nevertheless, the junction rule is a conservation in the sense that the amount of electrons flowing through this junction must be equal to the amount of electrons flowing through this junction. So if we analyze just the top junction here, the current flowing in is I1 and the current flowing out is I2 and I3. So I1 becomes I2 and I3. Looking at this bottom junction, the current that was flowing around reaches this point and flows in as I2 and flows in as I3 from the left, and then comes up and out as I1. And so what we see is that I2 plus I3 equals I1. And what we confirm is that there is only one junction statement, because this is the same as that. And that should hold true for conservation of charge. If there are only two junctions, then there is only one equational statement. Now, obviously, we can stick to just using Ohm's law to solve simple series circuits like this, because there is only one current, and there is, even if there were multiple resistors, it's a simple addition. Where Kirchoff's rules become valuable is when looking at complex circuits. This would be the beginning of a complex circuit, but a complex circuit in this sense would often have multiple power supplies, multiple loops, and usually have a much more complex look to it overall. But this starting circuit here is a good place to just get your bearings on what the process will be for using Kirchoff's rules, both conservation of energy and conservation of charge, in order to analyze the solution. And really, what it's all about is following both rules. And as I saw with this circuit above, we know that I1 is I2 plus I3. We've already written that down. But it's also true that there are closed loops that then follow the loop rule, as we just stated. So if I identify the loops, there's a loop here on the right that goes from the battery around in this closed section that would operate regardless of whether or not this resistor was working. So there's a loop here. There is also a loop here. Now I'm going to label it as from the battery going this way, going around this way. And then the third loop is actually a fact that if I remove the battery, these wires would still stay connected. And so there's an outside loop that I'm going to go ahead and label as saying going around the outside in this direction. Now when it comes to the loop rule, we have to remember that following the current in the direction of current across a battery as proper, then the battery is adding voltage. As I go across the resistor, then the resistor is removing voltage. And this is the statement that we wrote down previously, right? The resistor is removing voltage. In other words, it is utilizing the energy. So the entire sum across the entire circuit is equal to 0 because the battery supplies voltage and the resistors take it away. They utilize the energy. What's so important in terms of conservation of energy is that the resistors must use all of the power that is supplied. There cannot be any left over. And the same thing is true when looking at a more complex circuit like this one on our right. When I analyze the right-hand circuit, the right-hand loop, if I think about starting at this point here, then I can say from that point, the sum across the entire loop is 0. So I go across and I add V for the battery, which is applied at I1, but there's no resistor, so I don't worry about that, and just add the voltage. At the junction, I transition from I1 to I2, but now I'm moving across R2. And so I'm losing voltage flowing in the proper direction of current as I2 times R2. I close around the loop, and I find that back to this junction, I've completed my circle. So this would be our first loop statement. Secondary loop statement, right, would be starting at this position going this way, following the current, right? And so again, 0 equal to the voltage being added at the battery on I1. Turning left at this junction at the top, we go across I3, and we lose voltage according to R1. As we close the loop down across here, we find no additional resistors, so we're back to the beginning, and that loop is closed off. The third loop is the outside loop, which does not contain a battery, so we have to be clear on how to handle that. It's important to note that the conservation of energy holds regardless of whether or not there's a battery or not. So if we're looking at this outside loop, starting here, following around in this loop in this direction. As I go across R1 by I3, I'm going in the direction of I3 across R1, which means that the resistor is doing exactly what it should be, right? Taking away the energy. But as I transition across from I3 to I2, I find that I can't change the direction of my loop, and I've already identified the direction of my current as going in the opposite direction. So as I trace this loop, I need to be clear that as I look backwards across the resistor, I'm actually doing the opposite of what the resistor would normally do. In other words, I'm adding voltage as I2 times R2. And this is why this statement is still able to hold, in the sense that the R resistor is removing voltage, and in technicality, the R resistor, R2, is actually adding voltage because we're tracing this loop backwards. And you can think about this logically if you go back to your simple circuit over here. If I were to trace the loop in exactly the opposite direction, then as I go across the resistor in the opposite direction of I, the resistor would be adding voltage. But if I go across the battery backwards, then I'm actually losing voltage. So the sheer act of tracing a loop determines whether or not these signs invert on our original statement. So as long as I'm going in the direction of the identified current, I'm adding voltage with batteries and removing it with resistors so that my conservation can hold. But if I trace the loop this direction, then these turn to negative V and positive IR, and V equals IR still holds. So the conservation is true as long as I identify that, and that will happen as the circuits get more and more complex. As they get more and more complex, there will be more and more junctions, which will result in multiple loops, and eventually you'll end up tracing loops where you're going both forward and backward across resistors and batteries. And be careful to add voltage when you're going in the direction of current across batteries, and take it away when you're going in the opposite direction. And the reverse is true for resistors. If I'm going in the direction of current, I'm reducing the voltage, and if I'm going in the opposite direction of current, then I'm adding voltage. Nevertheless, what I'm able to do is take a complex circuit like this and generate a set of 4 equations. And what I note is that I have 1, 2, 3 unknowns, and so I'll need at least 1, 2, 3 equations to solve. I'll need one that contains I1, I2, and I3, and one that contains I2 by itself, and one that contains I3 by itself. And we see that here I can solve this set of equations using just these 3, and then I would know I2 and I3, and I can finalize this final loop. Given this set, the rest of it is simply algebra, system of equations, combining in order to find the unknowns. There will be multiple examples posted for you to practice.